So in the last lecture, we derived the potential energy function, and via the work, we know that this is equal to, actually this was a minus, we had minus that difference, and that's equal to K final minus K initial. So we have minus U final plus U initial equals K final minus K initial, and so this gives us K final plus U final equals K initial plus U initial, and this says that the kinetic energy plus the potential energy is always the same at every point in the path of some object. And so we can say that this is the initial energy equals the final energy, or that energy is conserved. The combination kinetic plus potential is the total energy, or more specifically, the total mechanical energy of a system. So to be specific, we also showed that the potential energy of an object of mass m, the gravitational potential energy is mgy. So we could do some example where we use conservation of energy to solve problems we've seen before. So specifically, an object that's dropped from some height h, we want to find the speed with which it hits the ground. Right, we can use the kinematic equations, of course. We can use work equals delta K, and now we can use conservation of energy. So from the perspective of energy conservation, this looks like, so we want to build this kind of an object. So we ask, is there initial kinetic energy? And the answer is no, because the object is not moving. Is there some initial potential energy due to gravity? And the answer is yes. We need to find the height, and so we can say that the total energy of the object of mass m is mgh, mg times h, and that's the total energy it will have when it reaches the bottom, but in a different form, right? The questions we're asking is there a speed? And yes, of course, it hits the ground with some speed, so we have some m over 2 unknown speed squared, that's an unknown quantity, plus how much potential energy we have. Well, the ground, if the height here was h relative to ground, that's 0, then we can say y is 0, and so there is no final potential energy, no final gravitational potential energy term. And so that's what energy conservation looks like. So of course, V is equal to 2gh square root. And if it's the speed, then it's just that. But if it's the vertical component, then we choose negative. That's the y component. That's the speed with which the object hits the ground. We could have, again, you can compare to using work equals delta K. So the delta K is final minus initial. The final is 1/2 m times unknown V squared minus the initial, which is 0, so it looks like that. And the work is the integral of the force over the distance, and it's mgh. And so it looks just like conservation of energy. So of course we'll get the same answer. We could do a problem where we launch the object straight up. So here we are launching the object straight up from ground, V0, and we want to find how far up it goes, and we want to use conservation of energy. So if we do that, then there's no height, so there's no mgy, but there is some initial kinetic energy in the form of 1/2 mv0 squared, and then it reaches some maximum height when there's no kinetic energy, so the potential energy is mg times that y, and so that y is equal to v0 squared over 2g. Right, and that's the height it reaches. From the perspective of work equals delta K, what does that look like? Well, the delta K side is the final kinetic minus the initial, so we have 0 for the final minus the initial, which is 1/2 m times v0 squared. And the work is the work done by gravity. It's the same work because it's the work over some height y, which is unknown, but it has to be negative, right? Because gravity is slowing the object down, and so it looks like that. And of course, we end up in the same place, but we have minus signs. So y is equal to v naught squared over 2g again. And of course, we could have used kinematic equations, but that's takes longer.